Hi, my name is Gleb, and I'm going to talk about the paper Sparse PCA, Algorithms, Adversarial Perturbations, and Certificates. It is a joint work with Tommaso, Pravesh, Kothari, and Steurer. So the Sparse PCA problem, the instance of Sparse PCA problem is a matrix Y with dimensions n by d. It is a sum of rank 1 matrix and standard Gaussian matrix W, and the rank 1 matrix it is a product of some positive number root beta, which is called signal strength, a Gaussian and dimensional vector, standard Gaussian and dimensional vector U, and a k-sparse unit d-dimensional vector, where by k-sparse we mean that it has most k non-zero entries, and we assume that the entries of W are IID, standard Gaussian variables. So the goal is to recover vector V0, more formally to find the vector V hat such that the squared correlation with of V hat and V0 is close to 1. It's not difficult to see that the sign of V0, there's no information about the sign of V0 in Y. So that's why it's impossible to recover the sign. But if beta is large enough, it's possible to find a vector V hat, which is correlated either with V0 or with minus V0. So, and the algorithms which solve this problem, we start with the exhaustive search algorithm, which just returns the maximizer of the sparse quadratic form. And it outputs the vector which is highly correlated with V0 for beta larger than k over n plus root k over n up to some logarithmic terms. And this algorithm is optimal, but of course optimal in up to some log vectors, but not, of course it is not efficient because we need a brute force search over the all subsize k set of size d. And what about efficient algorithms? So here we distinguish two regimes, the so-called weak signal regime and strong signal regime. So the weak signal regime is more interesting because it exploits sparsity. And strong signal regime, in the strong signal regime, the principal component of Y is related with V0. And that's why the standard singular value decomposition already works here. And in the case when SVD doesn't work in the weak signal regime, if we assume that beta is larger than k over n, then we have several algorithms. So the well-known algorithm for this problem is diagonal thresholding. Another well-known algorithm is the basic semi-definite programming relaxation, the sparse PCA problem. And similar to basic SDP is the sum of squares of constant degree. So they all work if beta is larger than k over n, again up to log vectors, which I ignore in this talk. So this problem is well known, is well studied, and the complexity picture seems to be clear and quite simple, but it is not the case if we add an adversarial matrix E, which can depend on anything, for example, W, on U, on V0. And the only restriction that we use on E is the bound of entries. Also, in the rest of the talk, we use the assumption that beta is larger than 1. Just for simplicity, it is not necessary for the analysis, but it simplifies the analysis. And the goal again is to find a vector such that the squared correlation is close to 1. And then what constraints should we enforce on E? So the trivial observation is that if entries of E are too small, then it's not interesting. The effect of E is negligible. But if the entries are too large, then we can just remove the signal just by taking minus root beta U transpose E. We can remove the signal. And it's not difficult to see that. So then we take a bound which is close to the second case. so close to the maximal possible magnitude of entries of E. So it's not difficult to see that if we allow a log vector, if we take E with entries up to root beta over k by log d, then we can remove the signal. So a bound root beta over k is reasonable because it's close to the optimal one, and also it's reasonable because in this case, V0 is close to the k-sparse vector, maximizing the sparse quadratic form. So again, exhaustive search works in this case. Information theoretically problem doesn't change. And exhaustive search has the same guarantees as in non-robust case for such values of for such magnitude of the entries of E. So what about the efficient algorithms? This is a picture for non-robust sparse PCA, and for robust, we see that the diagonal thresholding and SVD no longer work. So if we take E with entries of magnitude root beta over k, so diagonal thresholding and SVD do not output vector close to V0, but SOS and SDP they also work in the presence of the adversarial matrix E. And then there is a question. So why do some algorithms succeed even in the presence of adversarial perturbations? And why do other algorithms fail in the presence of adversarial perturbations? And so our observation is that algorithms that come with certificates of sparse quadratic forms are robust. So what do we mean by this? So again, here is a problem so the optimization problem of maximizing the sparse quadratic form. So, and even if we can, so it is unlikely that we can solve it efficiently, but what we can do, try to do efficiently, is to find some upper bound on this value. And the common approach to do this is to use convex relaxations, or more precisely, we use the sum of squares relaxations. So sum of squares hierarchy is sum of squares algorithms is a family of powerful algorithms which can relax to solve relaxations of systems of polynomial constraints, polynomial inequalities. It is based on semi-definite programming, and under some mild assumptions, if you have a system of m polynomial constraints and n variables, then degree t SOS relaxation can be solved in time n plus n to the O of t. And sum of squares is known to capture the best algorithms for many average case problems, including planted clique, tensor PCA, and many others. So sum of squares algorithm actually does not return, for example, for sparse PCA, it does not return a vector. It always returns a so-called pseudo-distribution. And just to recall the definition, a pseudo-distribution of degree 2t is a linear functional over polynomials of degree at most 2t, such that its value polynomial 1 is 1, and its value on squares is non-negative. And then a theorem, informal formulation of this theorem, that given a system of polynomial inequalities, for polynomials of degree at most 2t, degree 2t sum of squares algorithm finds a pseudo-distribution that satisfies this system of inequalities. And what does it mean? It means that for any sum of squares polynomial which is a sum of squares of other polynomials, h, and any subset of this system, if the degree of the product of these polynomials is less than 2t, then at most t, then the value of this functional pseudo-distribution is non-negative. So, and then how to obtain a vector from a pseudo-distribution. So sometimes it is tricky, but for this problem, we can simply take a top eigenvector of the pseudo-distribution of XX transpose, of polynomial XX, a matrix of polynomials XX transpose. So what about Sos certificates for robust sparse PCA? So if we write down the optimization problem of maximizing quadratic form, we can also write it. We can also formulate it in terms of polynomials, polynomial optimization problem. So we can just introduce the indicator variables with sparsity constraint. And the meaning of these SI variables, so it is 1 if I is in the support of B, and 0 if I is not in the support of B. And then we can consider the sum of squares relaxation of this system. And now let's let B hat be the solution of the degree T sum of squares relaxation. And then what we can do in the sum of squares, so we can write the following inequality just by multiplying y transpose y by v0. On the other hand, we have similar inequality with which we can obtain by multiplying y transpose y by v hat. Also, we have some cross terms. In general, we cannot ignore cross terms, but in this talk, we assume that beta is larger than 1, and under some mild assumptions, we can ignore cross terms. So let's ignore them. And then by the choice of v hat, we see that the left-hand side of the second inequality is at least the left-hand side as large as the left-hand side of the first inequality. And then we can just simply get the following bound. So as a conclusion, we see that the result depends on the upper bound that the algorithm can certify. What does it mean? It means that any pseudo distribution of degree T that satisfies, if we get a bound on any pseudo distribution of degree T that satisfies the system of polynomial constraints, then we get this upper bound is called the certified upper bound, which sum of squares of degree T can certify. So, and for the matrix E, for the term with E, the bound is quite easy because already the constant degree sum of squares can certify this bound. And then recall that we assumed some upper bound on the entries of E. And using this bound, we get that it is significantly smaller than n times p. And recall that, so we have this 1 over beta n factor in front of this big O. That's why we can assume that if beta is, if E is small enough compared to beta over k, the squared entry, maximal squared entry of E is small enough compared to beta over k, then it's enough only to get, then the term is with E is small, and it's enough to get the certified upper bound on the sparse quadratic form of W, of the Gaussian matrix W. So in the weak signal regime, if beta is larger than k over n, so one can show that the constant degree sum of squares can certify with high probability the following bound up to log factors k over k by root n, and in this under this assumption on beta, it is much smaller than beta, and again we get, so in this case, the high squared correlation, and it matches the best known guarantees in the fragile settings. So in this case, the complexity of the problem didn't change, at least for efficient algorithms. For polynomial time algorithms, we get the same guarantees as in the non-robust case. But for the strong signal regime, the situation is different. So here, degree T sum of squares can certify with high probability the following bound with d over k to the 1 over t. And also it has additional constraint that d is larger than n to the t. And this constraint we didn't see in the non-robust settings. So we get this bound, and it's not difficult to see that these guarantees are strictly worse for constant t these guarantees are strictly worse than the guarantees of simple SVD. But recall that SVD doesn't work in robust settings. And so for constant t, it is strictly worse. And for larger t, sum of squares, for t larger than constant, sum of squares is no longer polynomial time algorithm, but it approaches information theoretically optimal bound for t logarithmic. Okay. So again, in the fragile settings, the algorithm is worse than SVD, has worse guarantees than SVD. And so is it just because the algorithm is bad, or do we have an evidence that we cannot do better in robust settings? And so there is some evidence. So we can use lower bound based on low degree polynomials, which is closely related to the pseudo calibration technique for sum of squares, for sum of squares lower bounds. And what do? We construct a distribution over the adversarial matrices E, such that if we have an instance of the robust sparse PCA problem Y with this E, then low degree polynomials cannot distinguish this instance from just a standard Gaussian matrix. If D is smaller than n to the t, or more precisely, if D is smaller than n to the 0.99 t minus 1. So if D is significantly smaller than n to the t, then polynomials of degree at most n to the 0.001 cannot recover a vector with constant correlation with the 0. So and here we observe a statistical gap between robust and fragile efficient algorithms in strong signal regime. Recall that we don't have information theoretically, the problem doesn't change. So information theoretically, we do not see any similar effect. This is only a computational issue. Only this is a thing we observe only if we look at the reasonable models of computation and restrict, for example, the degrees of, for example, we look at the polynomial distinguishers or polynomial estimators, and we restrict the degree somehow reasonably. And then we see that there is a really difference between robust and non-robust sparse PCA in the strong signal regime. So very informal, brief sketch of the idea, how to construct this family, this distribution over the adversaries is consider the following problem. So given an n-dimensional hyperplane in dimensional space that contains a vector z0 with IID entries such that entry is large with probability k over d, so reasonably large, and such that the first 2t minus 2 moments of each entry coincides with moments of the standard Gaussian distribution. And the goal is to distinguish this hyperplane from a random hyperplane. So computation of low degree moments cannot, I mean, the informal explanation of why this problem is hard for d smaller than n to the t is that computation of low degree moments cannot help us to solve the problem, and we need at least n to the d plus n to the t samples to estimate the 2t moment of a Gaussian vector W. So this is the idea behind this construction, and how is it related to the robust sparse PCA problem is that we can write the instance of this hyperplane problem as an instance of robust sparse PCA problem. So this is a special case. We can write it as a special case of robust sparse PCA problem, and we get this lower bound for robust sparse PCA. So also we have some other results. So for example, using certified upper bounds, we show that in a big signal regime, basic SDP algorithm matches the guarantees of all non-polynomial time algorithms. And this result is interesting also for non-robust sparse PCA. For example, there is an algorithm called covariance thresholding, which was known to be strictly better than both diagonal thresholding and SVD in some regimes. And we show that basic SDP actually has the same guarantees in this regime. So also we provide a family of sub-exponential robust algorithms based on sum of squares, which match the best known guarantees in big signal regime. So previously known algorithms with such guarantees were non-robust. Also, we provide some other algorithms and lower bounds based on low degree polynomial techniques. So thank you very much for your attention.